Next type of bonding on hand we have is ionic compounds or ionic bonding. Ionic bonding is pretty simple that it is, as the name suggests, it is made up of ions. But how do ions form? And it's a process which is also explained in this pink portion. So the electrons involved in the formation of ions are those of the outer shells of atoms. Metals, as I've explained earlier, that they tend to lose their outer shell electrons to become positive ions. We also call them cations. In doing so, they achieve more stable electron arrangement of the nearest noble gas, right? For example, if we talk about sodium chloride, then you would see that sodium can easily lose one electron in its outermost shell, and then sodium ion, which will look like this one after that, will have the electronic configuration of the nearest noble gas. If you look at this electronic configuration, this is actually 2,8, and 2,8 resembles to neon in E, which is the nearest noble gas. However, the actual configuration was 2,8,1, which was the actual configuration of sodium. But now it's not Na anymore. We write it as Na positive, so we call it a positive ion. A positive ion is formed by the loss of outer shell electrons. It can be one electron, it can be more than one. Generally, atoms of non-metals gain its electrons to become negative ions. So the atom electrons that were lost by the positive ions or metal atoms are gained by the non-metal ones, and they become negative ions. Again, in doing so, they achieve the stable electron arrangement of the nearest noble gas of the periodic table. In this case, we talk about chlorine doing so. If you look at it, chlorine has the configuration of 2,8,7, 2 electrons in first shell, 8 electrons in second shell, and 7 electrons in the third shell. Now, as soon as sodium loses an electron, that electron would be gained by chlorine, and it would then become a chloride ion, the configuration of which would be 2,8,8. If you look at this configuration of 2,8,8, you will find the configuration similar to argon, Ar, nearest noble gas. However, we show it by a negative sign on chlorine, so it's a chloride ion. So the formation of positive and negative ions actually produces for us the stable arrangements of nearest noble gas of both the atoms. For sodium, it was neon. For chlorine, it is argon. Now, when these ions are formed, the positive ion and the negative ion, then they are going to help to one another in form of this lattice. The positive and negative charges would be surrounded by each other. We call it a giant ionic lattice. And this lattice stays in this form because they have very huge attractive forces for one another. We call these electrostatic forces of attraction. Remember, when we use the word electrostatic, that means that we're talking about unlike charges, negative attracting positive, positive attracting negative. Now, the features that are common to ionic bonding would be metal atoms always lose their outer electrons to form positive ions. Number of positive charges on a metal ion is actually equal to the number of electrons lost. Non-metal atoms, with the exception of hydrogen, will always gain electrons to become negative ions. Again, the number of negative charges on a non-metal ion is equal to the number of electrons gained, so it's pretty much similar to metal. So metal and non-metal behave almost in the same way. The only difference is that one of them is losing, one of them is gaining, metal and non-metal respectively. So in both cases, the ions formed have a more stable electron arrangement, usually that of the nearest noble gas to the element concerned. Ionic bond, which is also known as electrovalent bond, second name, result from the attraction between oppositely charged ions, electrostatic force of attraction in other words. So in the end, we'll get a structure like this. There are a couple of more examples explained over here. Let's take a look. Magnesium has 2 electrons in its outermost shell as it is in group 2. Oxygen has 6 as it is present in group 6. Magnesium is a metal, will lose 2 electrons. Oxygen is a non-metal, will gain those 2 electrons. Now, as you can see, magnesium is shown with a cross. However, the oxygen electrons are shown with dots. And in the end, the oxide ion actually has 6 dots, its original electrons, and 2 crosses, this one and this one, the ones it has gained from magnesium. Hence, the -2 charge on oxide ion, the +2 charge on magnesium ion. When these two combine, it forms magnesium oxide. In a similar way, calcium chloride, CaCl2, can also be formed, as calcium also belongs to group 2, can lose 2 electrons from its outermost shells, shown in crosses. Chlorine, however, is present in group 7, and it has 7 electrons in its outermost shell. You can see 2 chlorine atoms are written over here. That's because when calcium loses 2 electrons, one is gained by one atom of chlorine, and the other electron is gained by the other atom of chlorine. That's how it is balanced. So chlorine has a +2 charge on it. So my bad, sorry, calcium has a +2 charge on it, and chlorine, which is now converted into chloride ion, has a -1 charge each. But as there are 2 ions, they will balance the whole charges system and will have CaCl2, the compound, calcium chloride. The compounds that are written over here in study tips, such as lithium fluoride, potassium bromide, are the ones that have been a part of past papers. Commonly, compounds with halogens have commonly been used for past paper content. So you can practice these compounds at home, such as lithium fluoride or potassium bromide. Other ones used in exams are sodium oxide, right? So these are the few examples that you can use for ionic bonding to practice more compounds. Remember, whatever the case may be, it would always end up in formation of positive and negative ions by loss and gain of electron respectively, and the lattice would then consist of ions attracting each other as they are oppositely charged, so they would attract each other by electrostatic forces of attraction. The only thing important over here, which is done in ionic bonding and not in any other kind of bonding, are these red arrows. You would see there are many red arrows used over here. Remember, when you use a red arrow in ionic bonding, it means transfer of electron. The tail of the arrow represents the atom which is about to lose the electron. The head of the arrow represents the atom which is about to gain those electrons. So the tail is usually representing the metals, and the heads are usually representing the non-metals. And you would see the similar thing in all of the red arrows in these diagrams. So that's how we are supposed to use arrows in ionic bonding, depicting the loss of electron with the help of the tail of the arrow and gain of electron with the help of the head of the arrow. So make sure when you're using arrows, you're using them appropriately. That's about it. That finishes up the topic of ionic bonding for us. As the name suggests, polyatomic ions, the word poly means many and atomic means atoms. So actually we're talking about ions, which consist not just one atom, like the previous examples, in fact consist more. For example, the ionic compounds that we have mentioned had sodium ions, potassium ions, magnesium ions, chloride ions, oxide ions. But there are sometimes ions that are made up of group of atoms, such as sulfate, SO4 -2, or nitrate, NO3 negative, or carbonate, CO3 -2. These are known as polyatomic ions. We may also call them compound ions or group ions. They are made up of atoms which are covalently bonded together, but they have a charge because they have gained electrons to make a stable structure. They might have a positive charge too, a polyatomic ion with a positive charge. An example can be given for ammonium ion, the formula for which is NH4 positive. If we look at some of their structures, and let me tell you that drawing of these structures is not a part of IGCSE. This is just for a better understanding. you would see that one carbon is in the center, 3 oxygens are aside, carbonate, CO3 negative 2. For sulfate, the sulfur is in the center, all 4 oxygen atoms are on the sides, negative 2 charge. For nitrate, nitrogen is in the center, the 3 oxygen atoms are on the sides with a negative charge. And for ammonium, there is nitrogen in the center and 4 hydrogen atoms on the sides with a positive charge. So these are some polyatomic ions. There are a specific number of polyatomic ions which are a part of your course. Ammonium as positive, hydroxide, nitrate, hydrogen carbonate, sulfate, carbonate, and phosphate. That's about it. As you can see, 7 polyatomic ions in front of yourselves. That's all you need to memorize or know for IGCSE course. That's about it. We'll add a couple to this list, but later on, not in these chapters. So,
Okay, sir.
you do not supposed to draw the structures or these models of polyatomic ions. This is just for information. So you are not supposed to remember any of this. The only thing you're supposed to memorize is the name of the polyatomic ion and the formula. For example, the sulfate ions have SO4 negative 2 charge on them. So there is a sulfur atom, there are 4 oxygen atoms, and there is a -2 charge on them. That's about it. If you can memorize this, this is good enough for the exams. So after all this discussion, chemical bonding is now all 3 types: metallic, ionic, and covalent. So let's go through different kinds of substances that we have faced. So all the elements are given in the periodic table. I'm starting to go with this mind map to give you a better complete idea or broader perspective about all the elements that we have discussed so far. All the elements are present in the form of periodic table in front of you, and usually that's also at the back of the paper. So these elements can be divided into 2 categories: metals, non-metals. Metals are mostly present on the left of the periodic table, and non-metals usually carry the right-hand side part of the periodic table. When metals combine with one another, they go with metallic bonding, and they form giant metallic lattices with positively charged ions and delocalized electrons, as we have studied before. So they produce giant metallic lattices. If we talk about non-metals, non-metals exist as separate atoms and they don't bond with anyone. We call them noble gases. This is only true for group number 8, as we have studied. If they bond with one another, the bonding is known as covalent bonding. And as I've explained earlier, covalent bonding is all about non-metal bonding with a non-metal. Now, covalent bonding can result in 2 kinds of components, or we can say molecules. It may generate simple molecules for us, the examples of which we did yesterday. For example, ammonia is made from covalent bonding, or methane is made from covalent bonding, or water is made up of covalent bonding, or carbon dioxide is made up of covalent bonding. These are all simple molecules. These are simple, small molecules. They consist of very small number of atoms. You can easily draw their structures and show them or explain them. However, covalent bonding sometimes also produces giant molecular lattices, and this is something we haven't discussed yet. It's a part of this chapter, but it's a few pages ahead. So we're going to keep this one in particular and we'll discuss it later. So if we talk about compounds, compounds are formed either by the combination of metals with non-metals, and we have already explained that's known as ionic bonding. And ionic bonding always gives us ionic lattices, which are pretty giant, as they consist millions and trillions of positive and negative ions, oppositely charged ones in front of one another. We have seen some diagrams as well. Or compounds are made up of non-metals with non-metal bonding, which is covalent bonding, which actually results in these 2 kinds of molecules. The simple small molecules are the ones which we have practiced yesterday. Giant molecular lattices are the ones which we will explain after a few pages. So we are going to keep just this box for now, and we have explained the rest. So going with this mind map gives you a pretty good idea how different elements, be they are metals or non-metals, how they can bond, and what different kind of structures can you get out of it, as there are 5 different kinds of structures that we get out of it, and we've already explained 4 of them, and giant molecular lattices are the only ones we're keeping to be done later. So this mind map clarifies a lot of stuff, I hope.
Yes, sir.
Moving on, let's clear it up. At the bottom of this page lies one of the most important things IGCSE consider for their papers. By looking at it, it looks like a simple table 3.5, but let me tell you, I haven't seen a single year, a single season's papers without this table. So this is a very important table, and it comes out to be a part of your paper every single time. This paper is about differentiating between covalent and ionic compounds, and what kind of properties they have, and the reasons for those properties. Now, this is a very important study, as this is going to reveal many of the properties of different compounds. And whenever you're going to encounter an unknown compound in the exams, a few of the properties reported as a part of the question, you would instantly be able to make a guess about the compound, whether it's ionic or it's covalent. Let's go through those properties so it's easier for you to target your compounds from the questions about their kind of bondings. To begin with, we have ionic compounds on top and covalent compounds at bottom. What I'm going to do is that I'm going to not read their points completely. In fact, I'm going to compare them point by point. So 1 point from ionic and the same one from covalent, moving on like that, we'll keep comparing. So the first point in case of ionic compounds is that they are crystalline solids at room temperature. Remember, they had very strong forces of attraction because they had some positive charges, charged particles, and then they have some negatively charged particles. So the attractive forces were pretty strong. So they resulted in producing crystalline solids at room temperature. We call them ions, and the structure is known as lattice, as ions have opposite charges and they are next to each other. So the resulting structure is strong, hence solids. On the other hand, with simple covalent compounds, they are often liquids or gases because they are made up of simple molecules and the atoms are joined by covalent bonds, such as water is formed by 2 single covalent bonds of
Sir, you're
oxygen.
lagging a lot and I cannot properly hear you, sir.
Can you hear me now? Okay. So I was saying that water is made up of 2 simple single covalent bonds of oxygen with hydrogen. So this is the structure of water. This is a pretty simple small molecule. And as this is made up of single covalent bonds, so as I was saying, I was talking about ionic compounds being crystalline solids at room temperature because it was made up of ions in a lattice. Ions are actually positively charged and negatively charged particles in front of one another. So they have strong electrostatic force of attraction, which results in a solid structure at room temperature. On the other hand, the covalent compounds are either liquids or gases most of the time, and that's because they're made up of simple molecules, such as water is made up of 1 atom of oxygen covalently bonded to 2 atoms of hydrogen. This is as small as the structure can be. As the atoms are joined by covalent bonds, and these are simpler, smaller structures, they result in formation of liquids and gases at room temperature. So if we are to compare the attractive forces between their particles, it would be pretty strong for ionic lattices and in comparison to what the small molecules have in terms of covalent bonding. Moving on, as a second point, the ionic compounds have high melting and boiling points. As ions are attracted to each other by strong electrostatic forces of attraction, a large amount of energy is needed to separate them. On the other hand, the simple covalent compounds have low melting points and low boiling points. That's because the forces between the molecules, which we actually call intermolecular forces, are very weak. There isn't much energy that is required to move the molecules further apart from one another or convert them from solid to liquid or from liquid to gas, hence low melting and low boiling points. If we talk about the third point, for ionic compounds, they're often soluble in water. They're usually not soluble in organic solvents such as ethanol or methylbenzene or other organic solvents. That's because water is attracted to charged ions. Water has the capability to dissolve positively and negatively charged ions easily. So they are soluble in water. On the other hand, the simple covalent compounds are not very soluble in water. Very few of them are actually. They're mostly soluble in organic solvents such as ethanol or methylbenzene. That's because the covalently molecular substances dissolve in covalent solvents. For this understanding, we have a principle of like dissolves like. This means the substances that are made up of covalent bonding tend to dissolve the substances that are made up of covalent bonding. And ionic compounds, which are made up of ions, are usually soluble in water because water is attracted to charges. In the end, the fourth and last point states, and this is a confusing one and most used one when it comes to exams, ionic compounds conduct electricity only when they're molten, which means the ions are free to move, or dissolved in water, again the ions would be free to move, but not in solid state. So they are insulators as solids, but they are conductors as molten or aqueous solutions. In the liquid or the solution, the ions are free to move about. When they are free to move, they can carry the current with them as they are charged particles. So turns out they can conduct electricity in molten state or aqueous state. However, for simple covalent compounds, they do not conduct electricity at all. It's because there are no ions present to carry the current. In order to carry the current, the particle has to be charged, and there are no charged particles in the structures of simple covalent compounds. So that completes all the properties and their respective comparisons. If you have a question, please go ahead and ask. The chemical formulae of elements and compounds, 3.5. This one is
Sir, we can't hear you, sir. Or at least I can't.
Can you hear me now?
Yes, sir. I can hear you.
Okay, so chemical formula of elements and compounds. Now, in case of understanding how to write the formula of ionic compounds or elements, we need to understand a few things. There are a couple of formulas on the next pages. I'm going to change them a little bit for a better idea. But to begin with, we are going to go with the formulae of elements. If we talk about elements, it's easier to bifurcate them into 4 different categories, just like we have studied previously on the mind map. Take a look at this diagram, figure 3.3. The ones that are in dark blue color are the giant metallic ones that form giant metallic lattices. So they are pure metals. We talk about the ones that are yellow. They tend to form giant molecular lattices because they can easily form covalent bonds. Either that or they are metalloids. The ones that are given in gray color are simple molecules. They are the ones which are going to form simple covalent compounds with one another by bonding. We have studied most of them, like hydrogen, nitrogen, oxygen, chlorine, bromine, fluorine. However, something that is new over here is phosphorus P4 or sulfur S8. I'll clear them up too a little later. The single atoms are the ones which are on the extreme right-hand side of the periodic table and are all noble gases. So the simplest portion of the periodic table of the first few elements can give you a very good idea how we can bifurcate them into 4 separate parts, just like we have studied on the mind map previously. But this is just for the formulae of elements. For the formulae of elements, I usually don't worry much because it's just the start of the book. And as soon as you encounter the formulas again and again in the book, you automatically memorize them without having to go into a hassle of grammar. So don't worry. You need to just understand them a little bit, and with frequent consumption or usage of most of them, for example, N2, O2, Cl2, Br2, you'll automatically memorize these formulas. What's important?
Sir, sir, this is required, like we have to memorize it, right, sir?
Right, it's a requirement that you memorize them, but I don't ask my students to cram them because you'll automatically memorize them since you'll be using them a number of times.
Okay, sir.
Okay, so moving on, we have 2 kinds of compounds, ionic and covalent. So what we are going to do is that we are going to understand how their formula works. For ionic compounds, we have a set of formulas. For covalent, we have another set, so we are going to go with that. I'm going to skip this page and I'm going to bring you to the page where we have the formulas. There you go. On the next page after that, this is page number 77. On the top of the page in this pink portion, you'll find out how you can go with the formulas. Now, this is okay if you go with this, but I change it a little bit according to the ease of students. So what I'm going to do is that I'm going to rewrite these formulas for different kinds of compounds. So to begin with, for ionic compounds, the formulas work in this way. The groups 1 to 4, their valency, and remember the word valency is used for them. Why? I'll come to that a little later, would be equal to their group number. So if the group number is 1, their valency is 1. If the group number is 2, their valency is 2. If the group number is 3, their valency is 3, so on and so forth. But for groups 5 to 8, that's valency would be equal to group number minus 8. It's a little different than what's written over here. So what happens if I change it like this? For group number 1, the valency would be +1. For 2, it would be +2. For 3, it would be +3 according to these formulas. For 4, it would be +4. But for 5, according to this formula, it would be -3. For 6, it would be -2. For 7, it would be -1. And for 8, it would be 0. I hope now you understand why we call group 8 as group 8 or group 0. Why? Because the formulas turn out their valency to be 0. right? This is for ionic compounds. I'm going to erase it, and I'm going to talk about the covalent compounds for now. So for covalent compounds, we don't use the word valency. We mostly use the word combining power, that is equal to the group number, but we change it a little bit. Let me just change it a little bit. So only for groups 4 to 8. And this is the one for which we can go with 8 minus group number, right? So you would notice for covalent compounds, I've only taken groups from 4 to 8. That's because covalent compounds are only made up of non-metals. And group 1, 2, and 3 are mostly metals. Non-metals actually start from group 4, and they are present in group 4, 5, 6, and 7. So in that case, for group 4, for 5, for 6, for 7, or for 8, the combining powers would be 4, 3, 2, 1, and 0. So you'll find that group 8 is again 0. And these are the combining powers. Now, the question arises, what's the difference between the valency and the combining power? Now let me explain. In case of valency, what we mean is loss or gain of electron. Loss of electron results in a positive ion, and gain of electron results in a negative ion. In both the cases, the charges are usually written on the top right-hand side. Like we used to write sodium as Na positive or chloride ion as Cl negative. Now this positive and this negative are actually the valencies. And that happens to have valency because there was a proper transfer of electron. Sodium lost the electron, chlorine gained it. That's why the word valency. The word combining power is only used for covalent compounds. In this case, the electrons are not lost, they're not gained, they're actually mutually shared, as we have previously studied in covalent compounds. So when they are shared, we use the word combining power. The best part about combining power is that whatever numbers we use for combining powers, we don't put a charge beside them. We don't put a plus or a minus sign with them. So these are simple numbers. That's the major difference between combining power and valencies. All right? So that clarifies both covalent and ionic compounds. Let's try making a few formulas for practice so that you would understand what I mean and how I mean from it. Starting off with this example is pretty easy. As soon as you look at an example, two components, you would instantly know what you're supposed to work with. Aluminum is a metal in group 3, oxygen is a non-metal. This is an ionic compound, so they must lose and gain electrons. Aluminum can lose 3 electrons and hence can get a +3 charge or valency on it. Oxygen, being in group 6, can get gain 2 electrons and hence a -2 charge. Also, I've explained that in the previous formulas. The formulas I just wrote told us that group 3 has a +3 charge and a group 6 has a -2 charge. So I've used those numbers which I just explained in the formulas previously, and I wrote those numbers on top. What you're supposed to do is to cross multiply these numbers from superscripts to subscripts. Remember, superscript is a number which is written on the top, subscript is a number which is written at the bottom. And take a look, we have exchanged these numbers, but this time without the sign. So aluminum becomes 2, oxygen becomes 3 without the plus or the minus sign. All right, so that's how the formula comes into being. But there are a couple of steps that we need to understand from it. For example, if the formula has the charges like calcium and oxide does, calcium has +2 charge because it is from group 2. Oxygen has -2 charge, it is from group 6. Cross multiply the charges, but don't write their signs, so it's become Ca2O2. In that case, we need to simplify the ratio. This is a must in ionic compounds. As both the numbers are 2, they can be simplified into 1. And we don't write 1, so the formula simply becomes CaO. So these are the major steps. Take a look. First, write the valencies on top, cross multiply them, write the valencies at bottom, but this time without the signs after cross multiplying them. If it requires simplification, go for a simplification step. There you go, in the last step, you get the formula. So if you follow these 4 steps one by one, you can easily write many different formulas containing different metals, non-metals, or even polyatomic ions like this, right? So students can go ahead and practice these. For practice, what I usually suggest is different components. For example, you can practice aluminum and chlorine, or you may practice calcium and fluorine, or you may practice aluminum and nitrogen, or you may practice barium and oxygen, or magnesium and nitrogen, or sodium and nitrogen. So let's go with them. Aluminum is present in group 3, so it would have a +3 on it. This is group 7, so this is -1. We can simply write it as minus. All right. Cross multiplying them would give us AlCl3. 1 is never written, just like it does in algebra. So calcium is +2, fluoride is negative. Cross multiply them, you'll find CaF2. Simple enough. Aluminum is +3, nitride is -3 because this is in group 5. Cross multiply them, this would become Al3N3. But this can be simplified, so it would become Aln. Barium is present in group 2, oxide is present in group 6. Cross multiply them, this would become Ba2O2. Right, it can be simplified, so it would be converted into BaO. Magnesium
Is the 2 and 2 cancelled out?
Yeah, you can say cancelled out or simplified, whatever you'd like to call it.
Okay.
Right? Magnesium is present in group 2, so that's +2. Nitrogen is present in group 5, that's -3. So cross multiply them, you'll get Mg3 and 2. But as both 3 and 2 are prime numbers, they cannot be further simplified. The formula stays like this. Sodium is +1, nitride is -3. Cross multiply them, they would become Na3N and cannot be further simplified. So there you go. That's the way to do this, and you get many different formulas. But that's not it. Let's go with another kind of examples. What if we need to deal with a polyatomic ion like this? Now, for polyatomic ion, the charges are fixed. You need to memorize the polyatomic ions in order to get their charges. Otherwise, you won't be able to work them out. All right. So For sulfate, the charge is -2. In this case, it's -3 and 2. It's pretty easy to write 2 over here. But if we write -3 over here, this would actually interfere with SO4's formula. So what we do is that here we put in brackets and write 3 after the brackets. For every polyatomic ion, if the number is going to be bigger than 1, there are supposed to get brackets around them. That's the way to do it. For example, this is ammonium ion. This is carbonate ion. Now this is a combination of both the polyatomic ions. Now cross multiply the numbers. Ammonium would get a bracket because the number is bigger than 1. Carbonate will not get the bracket because the number is just 1. That's how the formula would be written for ammonium carbonate. Let's take another example. Aluminum may react with phosphate. Aluminum has a +3 while phosphate has a -3 charge. This time you'd notice that it might become Al3BO4 and actually brackets with 3. Now this 3 and this 3 can be simplified or cancelled out as per Ratio's rule. So it becomes AlBO4. Simply. No need of brackets because number has been cancelled out due to the simplification rule. I hope that explains it, right?
Yes, sir.
Okay, good. So these are the different kinds of formulas we may come up with in terms of dealing with simple ions or polyatomic ions in case of ionic compounds. Let's just save these examples and move back to the book. There are many different examples of ionic compounds given over here. Well, we are done with most of the examples that can give you an idea how we work with them. Let's talk about covalent compounds now. In case of covalent compounds, as you would notice, as he has written over here, we simply use numbers without the negative or positive charges. That's because we're talking about combining capacity in terms of sharing of electrons. Electrons are neither gained nor lost. So take a look at the example of carbon and oxygen. Carbon has the combining power of 4. Oxygen has the combining power of 2, being present in group 4 and group 6 respectively. Cross multiply these, it would become C2O4, like written over here. Simplify, it would become CO2. That's how the formula of carbon dioxide comes into being. And you can practice other formulas with it too. For example, sulfur or oxygen, right? Or nitrogen or oxygen. Sulfur has 2, oxygen has 2. Cross multiply, they become S2O2 or simply SO. However, this compound does not exist. There are reasons behind it, we'll study it later. For nitrogen and oxygen, this one is 3, this one is 2. Cross multiply them, this becomes N2O3. A proper formula. So it really depends upon their combining capacities, and in case of covalent compounds, you never use the plus or minus signs. Remember, we don't use the plus and minus signs because electrons are neither lost nor gained in covalent compounds. They're simply mutually shared. That's why. Right? So this clarifies for us the formulas. However, we are still supposed to go with the naming rules. So I'm going to keep the naming rules for